Ours is Moodle. So there you go. So what you would do, you'd get into Moodle. You should have the course listed. Now I've got everybody enrolled, so you should be able to access it. And then you go into the course, and there we are. All right, and there really isn't all that much going on in here. I just pretty much just post things in here. So here's the homework, okay? So the assignments are right there. So if we click on that, and if I've kept everything up to date, we've got homework 1, that's due Monday, October 2nd. 112, the statics project that we did in class here, and then the 122, that's supposed to be done graphically. Now the graph paper for that is provided. It's on the, now if you look at the packet, you've got the page that that homework problem is on is page 1. If you flip that, you will get to page 1A, and what 1A is a piece of graph paper with the problem on it, okay? So that's what's going on there. So sometimes I write up homework problems for you when they're right in the packet. I don't do it for all the problems, but I do it for a fair number, okay? So realize that. And my intent there is just to save you time, you know, so that it takes time to be writing these things up, I know. So I just put them in there for you on half of them or so are already written up. So have a look in there, you know, when you're doing homework, because some of them are all ready for you to go. Okay. And that's one of them. All right. You know, now if you don't have one of those write-up sheets, be sure you follow that homework format that we went over and that I handed out when you're doing the homework. Okay. So that's what's there. And I'll just keep adding things above this line as I assign it. Okay. Now, the other thing that's in here is a link. Now, this is primarily for the online students. It's right here. So if they click this link, what they can do is upload their assignment remotely. So if you're an online student, what you want to do is scan your assignment as a multi-page PDF. And be sure you do that, because the other file formats, be they whatever, Word documents or, you know, JPEGs or whatever the heck, those don't work so well on my end. So I do want multi-page PDFs. So you should have all 3 of these pages scanned as one PDF, and then you can upload it. Now be a little careful of the file size if you're doing that. You don't scan in color. That'll jump the file size up. There's a few other things that will cause problems with that. There are some file compressors available on the internet. They're generally free. So if you're having trouble with file size, you can compress the file. Okay, I've also got downloads for a lot of the projects and things that we do. So those are available. I've got test review downloads and things too. So these are the things that I hand out in class. So if you're an online student, you can get to those. All right.
We can turn it on by hand, right?
Yeah, I prefer it by hand, honestly. Paper is just easier to deal with for me. Okay, what's up with that? My goodness, look at all that. Okay, we'll go here. All right, so we took this problem this far. Why don't we finish it up? And then we'll look at the homework that I've assigned. So, do we have any questions on breaking those forces into vectors, into vector components, x and y? Are there any questions on that? We're doing okay? Okay. And we use vectors to model forces for this very reason, so that because we can break them up into x and y components. It's how we like to analyze things, okay? All right, so if we're good with that, and the other thing is, you know, keep in mind, if you got questions, ask them. I mean, you know, you're paying me to explain stuff, so it's fine with me. I mean, that's what I'm here for. So, you know, if you get any questions, let me know, okay? All right. All right, so the next thing we do here is we add them up, okay? So you just add up the two columns and get the total of the x and the y. Now remember, just standard arithmetic does not work with vectors generally, but it does work if you've got things all going in the same direction, which we do. So we can take the -60, the -30, and let's see, these are the y's, and then the -60 and add them up. And what we do is we get -150, and then we can take the 80, the 0, and the -120 and add them up, and we get -40. Okay? So we've added up the x's and the y's, and we get our resultant vector, -150i minus 40j. All right. So that's the total. All right. So what we can do now is we can find the magnitude of the resultant by taking the square root of the sum of the squares, and that's 155 newtons. And then we can also find the angle at which the resultant acts. This is all information that we might like to know. And that comes out to be the arctan of the sum of the y over the sum of the x. Remember to put your signs to include that in here. So I'm getting the arctan of -40 over -150, and that gets me the arctan of 0.2667, which is 14.9 degrees. Okay? So why don't you just sketch up that vector that you got. You got 155 newtons and when we calculated that angle, we got 14.9 degrees. Get the vector pointing the proper direction and just sketch it up if you would. Everybody doing all right? Okay. Now, I kind of warned you about this earlier on, is that you got to look at the vectors. You see, what happened here is we did the arctan of sum of fx over sum of fy, like this. And when what happens in your calculator when you do this, it divides -40 by -150. That's a positive 0.2667 is what it is. Now, your calculator's got a problem because it doesn't know the difference between these two things, see? Those will both get 0.2667. So it doesn't know the difference when it does this. So what it'll kick out is an answer that is always in quadrant 1 or quadrant 4. It gets you an answer of 14.9 degrees. But the deal with this is that vector is not pointing in the direction of positive 14.9 degrees is that angle it seems to indicate. What the vector's doing is it's going negative in the x and the y. And to get that figured out, if you just look at these numbers right here, see they're both negative. That means it's negative x, which is to the left, and negative y, which is down, okay? So you have to do this little bit here. You can't just rely on what comes out of your calculator. You actually have to look at the vector and determine which way it points from the components, the sign on them, okay? So just be a little careful of that. So, you know, you could say it is 14.9 degrees, but it's down left is what it is. You could also, if you want to be more formal about it, add 90 and 14.9 and get 194.9. I kind of like this method here because it's pretty unambiguous. You know, I got a sketch, shows an arrow and a labeled dimension. It's pretty clear what's going on with that, okay? All right, so just be aware of that with those arctans. You lose the sign on the arctan. There's two possible answers for every arctan. And your calculator is not smart enough to know which one it should choose, okay? So y'all okay with that? And when I think of this stuff, I think of it in a graphical, visual way, okay? And see, the other way to think about this, you know, if I go up left, go to the left, and then go down left, you know, I'm going to get that resultant there in yellow. I mean, that's what I did. I added those three vectors together. I did it analytically, so I just was punching a bunch of buttons on my calculator. But this is what we did earlier when we did this thing graphically, okay? And for this one, when we did it exactly with a calculator, we got, whatever the heck we got, 155 at 14.9 degrees. Okay, now this is what we did there. We broke that thing up into x and y components, the x in red and the y in green, and we just kind of added them together and got the resultant there of negative 40 and negative 150. All right. And when we did this, so that's what we end up with there, okay? Now, when we did this graphically, we got 155, so we did well with the length. When we measured that with a protractor, I think we got 15 degrees, but 14.9 and 15 are pretty close to my way of thinking, so that was pretty good. Okay. So the graphical answer got pretty much the same thing. A little bit of rounding error there, but that's fine. Okay. All right. So, you know, just don't lose sight of this picture in your mind when you're punching the buttons on your calculator. Just have a picture of what you're doing. That way, you know, you can avoid any sort of issues or trouble. Okay? So we got any questions on that? We're doing all right? Okay. All right. All right, why don't we have a look at those homework problems then? These are, you know, you can turn them in tomorrow if you like, or you can turn them in Monday too, because I decided to push it back primarily because of the online students. All right, so let's say we've got a light fixture here and we're going to hang it from a cable. Determine the force rating of the cable in newtons and pounds. Use a safety factor of 2. Use the proper homework format shown in class and include a sketch, okay? So that's what we're looking for here. So what you have there is you've got a mass, okay? That's what you've got. And you know, you don't do statics with masses. You do statics with weights, which would be newtons, okay? So what you'd want to do there is to convert the 400 kilograms into a weight. Okay, so we got any questions on that so far? Or do we got any general questions on this, I guess, to start? Yeah.
What is the safety factor?
Oh, yeah. Yes. Yeah, thanks. I didn't get to that, but a safety factor is something that engineers use all the time. And we don't want stuff to break, you know, obviously. And if stuff breaks, we're in trouble. And so what we do is we calculate a load based on our best analysis, And then we usually apply a safety factor to that. We make the load bigger than it truly is, than our calculations indicate. We do that to be careful, okay? So what I'm saying, so generally speaking, a safety factor reflects how confident you are of your analysis and what sort of conditions are going to have this object in, okay? So structural safety factors are usually on the range of about 1.4. So they design buildings and things to handle 1.4 of the maximum load they think they'll ever encounter. So they take their loads that they got and they multiply them all by 1.4. So with a safety factor, all you got to do is double whatever the load is you get. Just double it. And that's what you'd actually design this thing for, to be safe. Okay. So whatever answer you get, just double it. Other questions on this thing?
Do you care if you use scientific notation or just a number?
I don't really care about that. You know, just so it's clear. Just as long as I can, you know, reasonably read what you got, you know, we're good. Okay, so I don't care if you use scientific notation or not. So I think what you're going to do here, you're going to use mass times gravity is equal to weight, right? Because the weight is what, another word for that is a load. It's what we designed for, okay? So we just want to factor, just be sure to get that mass into a weight. And then what you'll do to get your load is you'll take the weight times 2. That's a safety factor, okay? That's all.
It wants both in units and pounds.
Oh, it does?
Yeah.
Ah, thank you.
So you calculate the force first and then
You change the.
Yeah, I would just calculate the force first, then convert it. You're going to get newtons is what you're going to get, then convert that into pounds. 4.45, I think. Newtons to the pound is what I think. You can look it up on the internet.
Yeah. It's
Okay. Okay. So just get it in both unit systems. Okay. So, got any questions on that? Any other questions? Okay. We're good. All right. Okay, now the next one there, what we want to do is, you know, remember I broke you up into groups. I had you just meet a few people and then answer some questions on that handout. You know the real reason I did that, right? Just wanted you to meet some people in your major. I mean, that was really all I was up to, okay? Just so you know a few people. I think it's just a good idea to do that, okay? So that was really my intent. So I'm not all that super particular on how you fill the handout, you know. Just get the bottom filled in. Now, some of you, like those of you online, you don't have an opportunity to do what we did in class, so don't worry about the top half of both pages if you're online so much. Just do your best as you can on the bottom half. So what was I looking for there? I was looking for projects you might work on, right? So, I don't know, a mechanical project, you might design a hydraulic jack or something. You'd certainly look at the loads with that. Civil, what do you got? You got bridges and things?
Bridges, buildings, roads.
Yeah, about everything you do has got loads on it. Yeah. What, chemical and bio, you might design a reactor vessel or something like that that has pressures inside. Something like that, okay. And then the sources of load are the things that, generally they're weights and things. Like if you're designing a building, this building was designed with loads that considered the weight of the structure itself as a load. That's called the dead load because it doesn't move around. The people and the furniture and the equipment and the things that do move around are called the live load. You've got wind loads, snow loads, earthquake loads these days. All these things are forces that you have to account for when you design things. So, yeah, it's probably a good idea. We should probably do that every time. Thanks. So when you do this, you want to have your name, the date, problem number, page number. I paraphrase the problem statement. I don't waste time copying it all down. I just paraphrase it. And then I got a little sketch, okay? And then I just show the work here, and I'll box in the answer over here. or answers, I might say on that one, because you got a couple to do. Okay. Okay, we got this one here is the last one. That's 122. Now that is on page, I think it's 1A of your packet. Just use a ruler with centimeter markings on it and a protractor. And just create that vector triangle is really all I want you to do on that. Okay. So it's pretty straight up. I mean, just have a point that's the origin, wherever that might be, and just draw in the vectors. So yes, F1, I'm not sure how long it is, but it's going to shoot over that away. And then F2 is going to go over this away, and then F3 is going to do something like that, okay? And that's all you got to do. Just put them together. And this isn't to scale. I'm just sketching this thing up. And then what you're going to do is you're going to connect the dots. You're going to start where you started and go down to where you finished. And that's the resultant vector right there. And you're going to measure it. You're going to measure the length of it, and that'll be the amount of force, and you'll measure the angle of it too. And fill those in at the bottom of the graph paper. Okay. So just something like that. That's really about all there is to it there. Just draw it to scale. You know, you've got, that's interesting. Oh boy. It's like I'm locking up here a little bit. So, you know, you've, I think it was 1 centimeter to what, 10 newtons or something? 15? Okay, thanks. Okay, so yeah, just be sure you're using the proper scale on that, okay? So, got any questions on that? All right, so that's just a little bit of an introduction there to vectors, okay? And just some of the things we do. All right, so that's step 1 here in the class, and then we've gone over some 2D vectors. Let's kind of look at the next step here. The next step is 3D vectors. Now, a lot of things we do, we can represent with two-dimensional vectors. You know, I showed you a picture of a truss bridge last time, and you could analyze that essentially with a series of two-dimensional analyses, all right? You could work at it that way. So this bridge right here, you've got 2 trusses on either side of the railroad tracks, and then you're going to have some connecting members running in between. But you can kind of break that up into a series of two-dimensional problems and work through it. And we build a lot of things kind of square, so that's very common to be able to do. But some things we can't do that. This is the Salem Convention Center here, and they've got those struts there that are holding up the roof. And those are going at kind of funny angles in 3-dimensional space. So if we're going to analyze those, we got to go into a 3-dimensional approach, okay? So let's have a look at that, and we're going to spend a little bit of time in 3 space, I guess they call it sometimes. So we'll do a few things here in 3-dimensional space. Okay, so we're kind of transitioning from the 2-dimensional vectors that we started with into these 3D vectors. Now the 2-dimensional vectors, I approach them kind of informally. You know, I look at them, I label the angles, and I use right angle trig to figure out the components. Three-dimensional vectors I treat a little bit in more of a formal sort of approach. I use a more kind of organized vector approach to do these. So this is on page 160. So we kind of have to come up with some definitions here. So we'll start off with three-dimensional space. We create three axes, the x, y, and z axes, and they're organized on what's called the right-hand rule. Now I've got that drawn in my usual format there on the left, where the x-axis comes out of the page, y to the right, and z up. I could also draw it like this. There's different ways to draw it. But however I draw it, the convention here is they conform to a right-handed rule. So if I point my fingers in the x direction, curl them in the y direction, my thumb points in the z. So there you go. So x, y, z with your right hand. Okay. So what we can do now, if we're in three-dimensional space, is define a vector in terms of its x, y, and z components. Having some graphics issues here. I don't know. So if I take a vector, which is represented by that little wire there, that piece of welding rod, and run it in three-dimensional space, what I could do, I can draw a box around it, okay? That's how I think of this. And the box extends from the lower corner of the box is on one end of the vector, the upper corner of the box is on the other. And that gets, I can make a three-dimensional box that that vector would fit into. What's happening here is that three sides of the box make up the x, y, and z components of the vector. Okay, so that's what we're doing. So what we're going to do to define the vector is we're going to call the beginning of the vector the origin, and then we'll have an x, a y, and a z axis that cover the whole box, or I guess I should say not axis, but components, x, y, and z components that make up the three sides of the box. And that's how I'll define the vector. Okay, so that's how I do that. Now what we're going to do is come up with a way to really analyze these so that we can pretty thoroughly cover these and do different things we'd like to do with them. Create force vectors, add them and get resultants, find components of force vectors on lines, and then eventually we'll find moments, which are twisting actions. And we'll do all of these things in three-dimensional space. Okay, so that's how you want to visualize that. The vector goes from one corner of the box diagonally to the opposite corner. All right, now a vector has any arbitrary length. There's also something called a unit vector. Now what a unit vector does is point in the same direction as the vector, but it's only got a length of 1. So a unit vector might look like that in orange there. It's pointing in the same direction as that vector A, but the unit vector only has a length of 1. So the way you create a unit vector is you take the vector A and you divide it by its own magnitude. That way you'll have a vector of length 1, because I've taken a vector with a magnitude of A and I've divided it by A. So that magnitude will be 1, but it will point in the direction of vector A. I think of it as like a direction pointer. Okay. Now Cartesian unit vectors, we got the x, y, and z axes. The unit vectors are I, j, and k. That's what we call them. They're vectors of length 1 that point in the x, y, and z directions. Okay. Did you all get this in math somewhere? That was a trig, or where'd you get it?
Started.
Yeah, started in trig. Okay, and you kind of build on it. You do a good bit of this in 254 if you've gotten there yet. Yeah. So, all right. Now, some of this is just notational stuff, but it's kind of necessary to organize this 3D stuff. It's a lot harder to visualize than the 2D stuff. So if I have vector A, that has its three components, AX, AY, and AZ. And I was just showing you that picture there. AX, AY, and AZ are the three sides of the box. You add those three sides together, you get the total vector, okay? Now I can express that differently though. It's not a real huge change here, but it's something you want to notice. Notice the vector marks are over AX, AY, and AZ. I can also break those things up into a magnitude, which would be A sub x, and a unit vector, which would be I, A sub yj, and A sub zk. I could do it that way. Not a big deal, but just a little bit different in notation. Okay, now the magnitude of this vector, A, is just the letter A. Now I think in a mathematics class they do it like this. Yeah, but for some reason in engineering we don't do those brackets. We just show the letter A, and that means a magnitude. Okay? So if I want to find A, how would I do it? If I know what that vector is, let's say it's whatever, 5, 6, 7. 5x, 5 in the x, 6 in the y, and 7 in the z. How would I find the magnitude of A? Yeah, right. Yeah, I can do the 3D theorem of Pythagoras. Okay? So I could go ax squared plus ay squared plus az squared. The theorem of Pythagoras works in 3D, so I can do that. So if I want to find that unit vector for A, and I don't think this is right in your handout, what I've got here, you're going to want to take AXI plus AYJ and AZK, and you're going to divide each component by the magnitude of A. Okay? That's how you'd find that unit vector A. Okay? Now, there's a real key relationship with these three-dimensional vectors that we want to get figured out. And what this is that anytime you look at any of these three components, you can connect them with the vector itself, and from that, you can get a right triangle. The easiest one to see on my sketch here is right here. If here's A sub z, here's A, and I can run a line across the top surface of that box. And that's actually a right angle. The z-axis is perpendicular to any line I run across that top surface of the box. And if I do that, I've got a right triangle. Okay? So what that means then, if I take the total vector A and divide it by, in this case, let's say A sub z, or excuse me, if I take A sub z right here, I reversed what I was trying to say there, A sub z, and I divide it by the length of this vector, total vector A, what I get is the cosine of the angle between the vector and the axis, because that's a right triangle. So what I'm going to do here is I'm going to take the right triangle that fits into that box. It's made up in this case by A sub z, A, and a line that connects the two across the top of the box. So that line up there and A sub z, so the line across the top of the box and A sub z make a right angle. I can pull that thing out, and what I'm going to have in there is the angle gamma down in the vertex. Okay? So cosine of that angle gamma is equal to A sub z over A. Okay? So these are called direction cosines. There's this key relationship that I could use to find cosine alpha, which is the angle the vector makes with the x-axis, cosine beta, which is the angle the vector makes with the y, and cosine gamma, which is the angle the vector makes with the z. So what I've got there is ax over a is cosine alpha, ay over a is cosine beta, and az over a is cosine gamma. Okay? So what I'm doing there is for that gamma angle, I'm taking AZ, and I'm taking A, and I'm running a line straight across, and that's a right angle. And so that's gamma. And so the cosine of gamma is equal to A sub Z over A. Keep switching that. There we go. And I can do the same thing for the angle with the x-axis and the y, which are called alpha and beta respectively. Okay? So that's an interesting little relationship there, because look what you got when you got a unit vector. You've got A sub x over A sub y over A, and A sub z over A. That's how you make a unit vector, right there. So when you've got a unit vector, what you have are the cosines of the angles that the vector itself makes with the x, y, and z axis. Kind of a useful relationship there. So if you can generate a unit vector, what you automatically have is cosine alpha, cosine beta, and cosine gamma, and that's all based on that right angle relationship, so I was just showing you. Okay? So that's kind of a keeper there. You want to remember that. We'll use that, okay? And I think I've got that on there somewhere. There we go. Next page there, okay? So if you've got some vector A, which would just be AX, AY, and AZ, what you do is you divide through by the magnitude of A, which is just the square root of the sum of the squares, and that'll get you those direction cosines. And that's also the unit vector. Okay? So the unit vector has the direction cosines embedded right in it. All right, now, what do we know? We know a unit vector has a magnitude of 1. So if we take the squares of those 3 direction cosines and add them up, that equals the magnitude, which is 1 squared, which is just 1. So this is a handy little relationship sometimes. If you know alpha and beta, you can find gamma using that relationship. Because you know that cosine squared alpha plus cosine squared beta plus cosine squared gamma is 1. So if you lack any one of them, you can find it. So you can't just have any 3 angles you want here. They're all relate to each other, okay? They're related by a function, okay? Okay, so the key facts here are when you've got a 3D unit vector, what you've got are when you look at the components of that vector, are the cosines of the angle that the vector itself makes with the x, y, and z axes. And those angles are called alpha, beta, and gamma. All right? So if you have let's say I tell you alpha is 30 degrees, what shape would that be around the x-axis? If I say alpha is 30 degrees, what do you know about that vector? What shape, what shape does alpha equals 30 describe around the x-axis? Not a prism, no. Think about every possible location of a vector if alpha is 30. What's that going to look like? If you plotted up every possible location. Cone, yeah. Okay? So the ideas of positive and negative get a little more tricky in 3 space because it's not quite as simple as it is in 2 space. But if I have an axis system like that, that's normally how I draw up these axes. So x, y, and z. If I plot up all the possible vectors with alpha equal to 30, I'm going to have a bunch of them, and they're going to look basically like that. And that's going to be 30 degrees, see? And that'll be 30 degrees. That's the idea, okay? So if you have that unit vector and you can find alpha, beta, and gamma, what you could do if you were good at AutoCAD is plot up 3 cones. And they should intersect on a line And this is quite a few years ago. This one had alpha is 69.3, beta is 111, and gamma is 30. And if you look at those cones, they all intersect on that line right there, and that's where the vector's at. Okay? So it's not like you can have an arbitrary 3 angles for alpha, beta, and gamma. They relate to each other. And they're related by that alpha squared plus beta squared plus gamma squared thing is 1. Okay? So to get them, the 3 of them to intersect on one line, you need to have a certain relationship between them. Okay? All right, let's have a look here. We've got just a little bit of time. Let's just start this thing here. This is page 180, I think.
You said 80 or 180?
180. So what I've done there, I've plotted up 3 vectors, F1, F2, and F3. Now F3 is the easiest of the bunch. It's just going straight up. It's in the Z direction. But F1 and F2 get the given angles there with the X, Y, and Z axes. So why don't you plot up, or excuse me, write down alpha, beta, and gamma for F1 and F2. What are they? Okay, so we're just looking at that sketch and pulling those angles off. Now they're just angles, they don't have signs, so just whatever you see for that angle, just fill in. So those red ones there for F1, so I got 131.9, 53, and 64 for X, Y, and Z. You all okay with that? Okay. Now we got just a couple minutes. Let's build, we good with that? Okay. Let's just look at how we do this. There's a very discrete series of steps that we would use to get the vector F1. Okay. So I've got those 3 angles, 131.9, 53, and 64. Now the key here is that I know that those angles, if I take the cosine of those angles, I should say, I get the unit vector. So I'll go cosine 131.9. Now notice that angle is bigger than 90, so when I take a cosine of it, I get a negative number. That goes in the negative x direction on account of that angle. Okay. And then I got cosine 53 and cosine 64. Okay. I just plug those in and run the numbers, and what I get automatically is a unit vector. That's a vector of length 1 that points in the direction of F1. Now that thing has a length of 1. Yeah, question there. Yeah. Yeah, there's a standard process for all of these. It's just, this is kind of the drill on how you do it. So you do use cosine for F2. Okay. Now I know that F1 has a magnitude of 500, and I know this unit vector has a magnitude of 1. So if I take the unit vector and I scale it up by 500, I'll get the force vector. Okay. So negative 334I plus 301J plus 219K. And that has units of newtons. So that's how you build a force vector if you know the angles. Take the cosine of the angles and get the unit vector, scale the unit vector up by the magnitude of the force, and that'll get you the force vector. Then I can take the square root of some of the squares just to check, and it comes back to 500, so that's pretty good. Okay, that's working. All right. Doing all right with that? All right, we're about out of time here. I'm going to give you a couple of these things to be doing for next week. It looks like I already typed this in, though the date isn't right. Oh, come on now. What is that? Is that the 3rd, I think, isn't it? Or is it the 4th? 4th, yeah, thanks, 4th. Okay, so 122 and 1... Hang on, did I already assign 122? Yep. Yeah. Okay, hang on just a second. So if I did that, I should definitely give you 132, and how about 131 also, just for fun? Okay, that's a good one. So 131 and 132, we'll make those due Wednesday, October 4th, okay? So only the 3 are due either tomorrow or Monday. This will be due later next week, okay? We good with that? We got any questions? Are we good? Okay, now we're in this room from here on. This is where we're going to be, okay? So we stay in this room.